My name is Fumeng. I'm a fourth/fifth year PhD student at Brown University. So I would like to talk about my intern work, which I did with PNL, where we introduced the concept of appropriate trust. And let's look at how do visual explanations foster end users' appropriate trust in machine learning. So I have three highlights for my talk. The first one is unfortunately not new, and I'm pretty sure you have seen a lot of this. We demonstrate that visual explanations improve end users' trust in an automatic system, and but we argue that trust must be appropriate. And last, we will show that the design of visual explanations affects users' appropriate trust. And up until now, I think I have said the word trust over 10 times. But what's trust? We only consider human-computer trust here. It is defined as the extent to which a user is confident in and willing to act on the recommendation, action, or decisions of an artificial intelligent agent. And appropriate trust is the alignment between the perceived and the actual performance of the system. And to break it down, appropriate trust relies on two aspects. The first one is system recommendation, and the second one is user decision. A system recommendation could be correct or incorrect, while the user could decide to follow or not follow the recommendation. If a user decides to follow a correct recommendation, or the user decides to not follow an incorrect recommendation, we say these are appropriate trust. While if the user decides to follow an incorrect recommendation, we say this is overtrust. Last, if the user decides to not follow an correct recommendation, we say this is undertrust. For instance, my trust in an iRobot will be my confidence in that it would just clean the floor, and my willingness to just do the work. I overtrust an iRobot when I think it would avoid hitting the wall, but it does not. And I undertrust an iRobot when I thought it would hit the wall and try to grab it, but it turns out it successfully makes a turn. Of course, in the real world, the case can be more critical and more complicated. For example, it could be a pilot operating an aircraft, and the pilot could decide to reject a recommendation from the system or follow the recommendation. And of course, today we are not going to study an iRobot nor an aircraft. We would only look at the end user's property trust in in classifier by visual explanations. And towards this goal, we designed a human subject experiment with three specific goals in our mind. The first one is we wish to study the relationship between users' trust in a system and visual explanations. And the second, we wish to quantify the effects of different visualization designs on users' trust in machine learning. And third, we wish to understand we wish to understand users' appropriate trust for proper usage of an automatic system. As experiment overview, we used example-based explanations, and we manipulated two visualization design factors. The first one is instance representation, and second one is spatial layout. And we measured the user's appropriate trust and also the usability of our visual explanations, as well as a little bit of individual differences. Last, the task we give to participants is where we ask them to classify leaves aided by the classifiers without visual explanations. So for the example-based explanations, we designed our own algorithm which we call it explicit rules. It uses a metaphors. It uses a metaphor where like we would like to use the shortest path in order to travel to a different state, which is probably not possible because we are all under quarantine today. Okay, if we wish to travel from Nashville to another state, we will take the shortest path and just stop at the border city. And all the cities on this path will be the examples used in our explanations. So in order to identify these examples, we built a k-nearest neighborhoods graph based on internal representation of a training set of the training set, and we construct a shortest path tree rooted at the input node. And we prune the tree and only keep the leaves on the passes and the leaves which may have a different class from the input node. And for these examples, we use two different ways to represent them. The first one, of course, if an image is available, we could just use an image to represent either instance. And the second, if we only have feature vectors, we could use a rows chart to represent a feature vector, and each sector in the rows chart is a feature. And in order to organize and arrange the instance and display the relationship between them, we use three different spatial layouts. The first one is grid, where we just sort instance within a column by their distance to the input node. The second one is tree. It's basically the shortest path tree, but we use a layered graph layout to draw the nodes. And the last one is a graph. It uses a force direct layout algorithm to arrange the instance by further considering the connections between them. Taking these two design factors together, here I'm going to show some examples of the visual explanations in our experiments. The first one is great for image-based explanations, and tree and graph. Next, I'm going to show those charts, grid, tree, graph. And these are 6 different visual explanations for the same instance and the same classification recommendation. And the task we give to participants is, remember that we just asked them to classify leaves. We give them a recommendation from the classifier on top, and they could have different visual explanations at the bottom. And we measure their trust in the classifier at their willingness to follow the recommendation and their self-confidence in the decision. And we ask 4 questions in order to quantify their trust. Will you follow this recommendation, and how do you feel about the decision above? Was the explanation helpful? And a trust meter where participants could adjust at any time to indicate the change of their trust. For the experiment design, we use a busy subject design where each participant finish all the conditions. They see different instance representations on 2 different days. It's basically we ask them to come back. On each day, they saw 3 different layouts and a control condition where no explanations was available. And in each condition, it's basically a combination of 3 spatial layout and instance representation. And in the control condition, they only have the instance representation and no explanation was given. And in each condition, participants finish a series of trial. It has It is a fixed order of correct and incorrect recommendation generated by a Monte Carlo algorithm, but we randomized instance within the sequences to counterbalance the ordering effects. And last, we recruit 33 participants from P&L. 16 of them did data analysis as part of their job at P&L, and we identify them as data analysts. As a summary of the experiment, we collect three metrics for trust. The first one is appropriate trust, and then the second overtrust, third undertrust, and then self-confidence. And we also had the perceived helpfulness of each visual explanation, and we also collected the records from the trust meter. And in total, we based our analysis on 7,128 trials. To guide our analysis, we asked 5 different research questions, and I'm only going to talk about 4 for today. The fifth one is a little bit hard to explain, and it takes a little bit long to explain it clearly. And we use bootstrap confidence intervals and effect size to quantify the differences. We built mixed effect models to account for individual differences, and the basic methodology is just we aggregate each participant's data and then subtract within participants to compute the differences. And last, I want to emphasize that we focused on summarizing all the confidence intervals, and we avoid making a single conclusion based on a single confidence interval. And for the first research questions, we want to confirm that our visual explanations are good. So we ask, do our visual explanations foster more appropriate trust? We did the subtraction, where we subtract the true condition from all the visual explanation conditions. And we found out that the effects are pretty strong. Like all our visual explanations largely increase appropriate trust, decrease overtrust, undertrust, and improve self-confidence. We further investigated the differences between the 3 spatial layouts. We did the pairwise comparison by subtract within different visual explanations. And we see that the effects are smaller this time, but for the image-based explanations, we found that the grid explanations are slightly more helpful than the tree explanations, which are slightly more helpful than graph explanations. For the rows-based explanations, the case are different. We found that tree and graph explanations, especially the tree explanations, seem to lead to more appropriate trust than grid explanations. And the third research question is, how did the two instance representations affect users' trust differently? This time we did the subtraction by subtract rows-based explanations from the image-based explanations. And we found out that image-based explanations outperform rows-based explanations on all the dimensions. So, in other words, the image-based explanations improved more appropriate trust, decreased more of overtrust and undertrust, and they also improved more like self-confidence, and the participants thought that image-based explanations are more helpful than the rows-based explanations. For the last and the fourth research questions, we want to investigate a little bit about individual differences. We measured three types of individual differences. The first one is if the participants are data scientists or not. And the second one is their prior knowledge, their familiarity with Leaf. And the last one is propensity to trust. We built mixture effect models where we use these three individual differences factors as well as the two experimental factors as the fixed effects. We use participants as the random intercepts to account for the correlation in observations within participants. We found that the strongest effects came from the two experimental variables, whereas that images explanations outperform the rows-based explanations, and having a visual explanation outperforms the control condition where no explanations were given. The only exception we found is that the non-expert users seem to have more confidence in their decisions. As I said that at the very beginning of our data analysis session, this is a single confidence interval, and we confirm this is true when we look at their participants' anecdotal feedback and free comments, where that the expert users report that they want more information in order to be more confident in their decision, such that here I would like to say that this might be true that the non-expert users seem to have more confidence in their decisions. And sorry, this takes a little bit longer to explain. To summarize my talk and give some takeaways, we would like to say that if the dataset is similar and the problem is similar, we would like to recommend a grid layout if the representation is easy to understand. And we would like to recommend a tree layout if the representation is difficult to understand or the usability is unknown. It is because that the tree layout gives a little bit more information about the relationship between the instance, while it is easier to read than a graph layout. And second, we think that understanding and trust are relevant but different. We don't think that participants understand how the algorithm operates because we did not give them such information, but they were still able to make good decisions. But we think that they must understand an explanation in order to trust the classifier. And last, we definitely recommend future research considering appropriate trust instead of simply measuring an increase in users' trust. Overtrust and undertrust should be avoided when investigating users' trust in machine learning. And thank you so much for listening. I upload almost everything to my own website, including video slides, supplementary materials, as well as a literature review documentation. Yeah, thanks again. I hope you enjoy the rest of your day.